Hello everyone, and thank you, Julian, and all the people organizing the event. I'm very glad to be here to talk a little bit about Rust, as already announced. And I'm focusing here on the open source landscape towards the safety critical projects. Yeah, so here again the introduction slide. A little bit about myself. I'm a firmware engineer at Infineon since about 8 years now. At Infineon I also run the Rust community, so I bring people together to discuss the Rust topic at Infineon to coordinate the initiatives on providing a common ecosystem and discuss also topics that are relevant to address some important topics as I'm going to discuss here today. I'm also a member of the Safety Critical Rust Consortium, which I'm going to mention also during my presentation a little bit more about, and also coordinate and organize the Augsburg Rust Meetup together with my friend Michael, who is sitting over there. So if you want to talk about it, then also you can talk to him, and you can reach me out over this context here. Before I start, then I want to invite you all for our next meetup in Augsburg. It's not far away. It's end of November, where we'll have a very nice presentation from a very special guest who is also sitting over there. So Christian Meusel will present his work about oxidizing step by step. And if you want to know a little bit more as a teaser about it, then go to him and discuss him in the breakout session. And if you want to assign to the participation, just use the QR code or open the web page. You can also find us in the Metrics channel, so you can be updated on the next outcomes. All right, but before we start talking about Rust itself, I would like to discuss a little bit what is safety about. So safety in the end, it's about people, it's about environment, and also about money, of course. So we want to have systems that do not destroy things around, so we want to protect people with equipment and environment. And we want to have, and safety also is about having systems that execute as they were designed to. And if they fail, they need to fail in a predicted way. So you need to know if this elevator simply breaks, it won't simply fall down and let people in get hurt. It will stop and will be open to get out within a safely manner, for example. And what can you certify? So you can certify many things. You can certify equipment, you can certify tools, and tools in different manners, also software tools, but also equipment as tools. And software, as I said, as well, firmware, chips, processes, professionals, they're very broad ecosystem of qualification for safety. And here we have some. So someone already mentioned here, automotive, avionics, railway, and this one I discovered when I was doing this presentation. Does anyone know this one here? It's about entertainment systems. So these stages that go up and down, like this one that Michael Jackson used to jump over the air in the Super Bowl presentation, for example. That's what it is about. But one thing that, since I'm going to talk about Rust, one thing that it needs to be clear is that these certifications, they are not related to a specific programming language, even if you're talking about software or firmware. So important things here actually for certifications or qualifications for safety is the tool-chain qualification and having coding guidelines to use in the process to show that you are following these best practices on the development. And the most used language for safety systems now is still C. And C has a very, very long and strong history in the industry. Started in the 70s created by Dennis Ritchie in the Bell Labs. And it passed through a long path here on providers offering compilers. And this is one interesting thing about C. There was the language, but there was no specification in the beginning, and many compilers were starting then producing, many companies were starting producing and offering C compilers, and the portability was a chaos, as you can imagine. And that's when it came along and said, hey, we need a specification for the language so we know what we are talking. And it evolved with the time, and the industry also created the famous MISRA C standard, and some other standards came along as well, and some big important projects started using. In the beginning, I think one of the great things that made C a success was the use in the Unix operating system, and then later on it also motivated the use on the Linux, which we already heard today about, and it keeps evolving. So C is very much alive and strong in the industry, but it has some issues, as we already know and we already discussed. Julian already mentioned before. We have till today recurrent flaws in different projects related to some issues that are produced due to this, one of the big weaknesses on the C language, that is the memory safety. And here is just collected a few of those, but I put it with a long timeline here to highlight that C has been along since a very long time period. And the industry evolved, as I showed, with tools and guidelines. And despite all of that, we still face these issues until now. So, and it's for sure more to come. So it's because producing software is not an easy thing. So, and having a language that gives you more support to avoid such problems here, like memory safety, which is being the main cause here of this, all these flaws. And as Julian mentioned, there was this talk, this report from Microsoft saying that 70% of the security issues of the CVEs that they were posting were about memory safety. So we need something new. The industry needs to go to the next level of software development. But then we need to stop and put things into place. I started talking about safety. Then I showed a list of security bugs, and I started talking about memory safety. You can feel, say, hey, this guy is trying to confuse me. So let's put the right things into the right place. We have security bugs and security requirements, let's say. And if you don't fulfill those requirements, you have basically a bug. And for security, for example, it's interesting and important to have sometimes entropy when you are calculating hashes or doing some key generation or validating some passwords, for example. On the other hand, in safety, this entropy is not good. You need to be deterministic. You need to meet the deadlines. You need to be to know the priority of your threads and processes. They might be at some point here divergent from each other, but one thing that is really common between them is that none of both sides wants to have memory safety bugs. No one wants to have a case where you're trying to read a value from the stack and the stack was corrupted by some other process, or you forgot to initialize your variable and then you're having a value to I don't know, apply to your PWM that is going to interact with some heavy machinery in the end, and you did not initialize the value and you know what you're going to apply on your PWM. So those things are in common. So it means that if we produce good quality software, we are both addressing safety and also security. And we are entering actually a new era of the software development. We see, we just heard from the European Union where we want to increase the quality of the overall products by the use of the CRA. In the US, they also have been mentioning improving the quality in terms of software security. And they mentioned systematically in the last 3 years here, since 2022, 23, 24, and 25, different organizations are being talking about memory safety in software in the US. So if you see here, just to mention some, NIST already listed Rust for one of the safer languages to be used. And the White House did a press release about the software that should be developed in memory safe languages. But why among the existing ones using Rust? Rust is not the only memory safe language around. We have Python, we have Java. Point is, Rust managed to combine some things that no other language combined now. So we have this memory ownership model that has a specific rule that allows you to have one single mutable reference and all multiple immutable references. And that makes possible to guarantee that you won't mess up with the memory in your code. So that's the starting point, but also Rust provides a strong type system. It's a new language providing new features that allow us to do some other types of strong abstractions without losing performance due to these so-called zero-cost abstractions. And these things here allow us to have a check of our code already in the compile time, where we get the error prior to even starting the tests. So in C, what we usually have, we will compile the code, we need to write a test, and at some time we will have some, we might have some errors, but you already spend a lot of time here developing all the tests that you need to run in runtime. So Rust also offers us the chance to do the so-called shift left, so you can run with run into the errors prior to the next phase here of writing tests. And with the language also, it comes with a nice developed ecosystem. So you have a compiler that is open source. The compiler, the project also has the core library and standard library that may be used in some specific cases here. I will talk a little bit more about. We have Cargo that was already mentioned, and it's, as we saw, it's very loved around the Linux community.
I'm not speaking for the Linux community.
Okay, sorry. Cargo is a package manager and a build system that comes out of the box here with the Rust project. And of course, it has a lot of crates that are the Rust libraries and binaries that are available from the community and can be used. So a typical architecture then, when you talk about Rust in embedded, it starts here on the bottom with the so-called peripheral access crates. And the nice thing about the peripheral access crates is that you can generate it out of the SVD files, and SVD files are already standard, common in the industry. And you have today two different tools that you can use to generate these packages. So one is the SVD to Rust, maintained from the embedded Rust community, and the other one is the SVD to Pack that is maintained by Infineon. And by the way, the maintainer is sitting over there, Oreste Bernardi, my colleague. And if you want to know more practical differences between the two of those, then you can talk to him in the breaking session. On top of that, we can develop then hardware abstraction layers. And one thing about that is nice with the hardware abstraction layers in Rust is that the embedded Rust community, they came up with a nice idea to use one of the nice features of Rust to creating traits that are kind of interfaces that you can establish, so you can develop your code on top of these interfaces, and you can decouple it from the actual implementation on the bottom, so you can facilitate in the portability between the code. And here are the embedded Hall traits that are developed and maintained by the embedded community, the embedded working group. And if you implement those, then there is really good chances that some other projects that are using those that will be easily ported to your chip that implements the Hall. On top of that, then you can also have a board crate. Board crate would be something that is not really always useful, but it might be interesting for you if you want to develop, for example, development kits, where you create the interfaces for some specific functions of your board, like you have a push button, you have an LED, you have a microphone, and you simply put the trait or the interface to this specific, let's say, asset of your board. And if you have another board which has the same assets, you can develop the application on top of this abstraction, so you can easily port between boards. This one here are the OSs and RTS. So in Rust we have already a handful of those. So here just to mention a few, and I think the most known are the Aereo OS, Arctic. By the way, Arctic, if you heard about Rust on Volvo cars, they used Arctic for that. Embassy, I think today Embassy is the most beloved one. It's about async in embedded, and TOC. TOC is really nice. It's also used by Google and Microsoft for some of the projects that they have in Rust. And there is one company that is certifying this OS here for safety critical. So it's a company called Oxide OS. If you're interested in that, you should take a look at it. And of course, on top of that, you can write your application in Rust. That, as I said, can then easily be ported, relying on this nice abstraction that you can have. And one more thing that is important to keep in mind. So when you talk about embedded, it's important to know which are the platforms that are supported by the compiler that is available. So in here in Rust, you have for low-level embedded, let's call it or bare metal. You have basically the most used ones from ARM. You have also RISC-V, and there are also new ones that are being added every day. So you can have a updated list in the Rustlang platform support webpage. Another thing that's also important to say about Rust in low level is I mentioned to you two things other than compiler is the core library and the standard library. When you are really programming low level Rust, so you don't have any operating system, you only works with the no stud. So it means that you're using the core library. The core library allows you to use the types, and you can use error type, the iterators, panic, assert. You can use even future and for async, atomic operations and traits. But you don't have the other parts of the standard library that are the allocation methods and some fancy types of libraries for file system, of course. So you need to be careful here that although Rust is very flexible in terms of application, you can go from low level up to the cloud. In the low level, you have only the core library available. All right, with the overview of Rust done, so let's get back to the safety part. So usually when you talk about developing safety software, you need to think about this V model. So it's a common standard in the software industry for safety to look into that, and also security. You can apply this model. We start with the requirements. You develop your architecture, design, you code. You then need to write the unit test of your code, integrate it, test it in the integration mode, and also write the acceptance tests. And everything needs to be traceable from one side to the other here. This part of this V model, you can argue, okay, this is completely independent of the language. But even there, you still have some tools that you can use for Rust. So for requirements management, for example, there are some interesting projects available in the open source community. You have Bazel, that's maintained by the Linux Foundation under the ELISA project. I will talk a little bit more about it later on again. Sphinx Needs. This is a Python-based requirements manager. A Lobster, that's one maintained by BMW. Anyone from BMW here today? No. Okay. And also Mantra. So Mantra is one of the example we have here. You can address the requirements here on this top and add. Oops, sorry, wrong one. This is not Mantra. This is about the diagrams. I have to speed up because I used too much time. So, so we have these projects here that can be used to produce diagrams, which are really important also to document your code. Documentation is a really important part. So you have basically Marmade and PlanUML that you can integrate with Rust crates in your project. They look like that. So here, this one is using Marmade, and this one is using PlanUML, and you can integrate nicely in the documentation generation. You have Mantra to go over the requirements. So in Mantra, it allows you to put this prog macros here that will allow you to do the requirements traceability and produce nice reports like that. So you can see here that you can check if the requirement was traced, it was covered by test, or was verified manually. So you have different ways to enter these values here. We have a nice blog post that was written here for the maintainer of that. It was partially developed inside Infineon, but it's now maintained by the original author. It's not at Infineon anymore. We have the coding part. In the coding part, we need, of course, the toolchain. And here we need to have the compiler certified. So here we have 3 vendors that are providing the certification of the compiler. But it's important to mention that the compiler is still open source. So we have AdaCore, Ferrocene, and Hitech. And Ferrocene here I would like to highlight because this is the one that is actually accessible open source. The specific, let's call it downstreamed, but it's still open source version for the compiler is available even in the certification mode. But of course, for the toolkit, for the quali kit, you need to then contact the vendor for that. And this one also was the base for the formal specification of the language. For coding guidelines, you can use Clippy, but of course you need to then come up with your own coding guidelines based on the Clippy rules. And if you are using unsafe Rust, you should use MIDI to help check your code for any undefined behavior. So MIDI is also used by the Rust compiler project itself. And if you are interested in model checkers, you can use Kani. We had a project at Infineon that used Kani for model verification. The coding guidelines, so we have Mizrahi already publishing an addendum where it correlates the guidelines of Mizrahi to the corresponding Rust, if the corresponding rule matches what Rust offers as a check already in the compiler. So you can, this is actually free to download, so you can take a look, and they classify here in the different modes, Rust for unsafe Rust and general Rust. And there is also this one from the French government about ANSI. This is mainly related about security, but unfortunately there's no specific Clippy checks or any tool still checking for that. And then for this side here, we have the specification. Yeah, so then let me just finish this one here.
Last slide.
And yeah, well, then I'll go. There is a lot of things to. Okay, I had a lot more to talk about. Sorry about that. So just wanted to say one thing. So Rust, safety critical and open source is not only about Rust. There are also other projects like in the SVD, Eclipse Foundation, and the Linux Foundation. And this thing I would like to end then my presentation with that. So Rust suits safety critical system, but there are still some gaps open. If you are interested in talking about safety critical in Rust, join the Safety Critical Consortium. It is free and open to anyone. You don't need to pay anything. And so open source software is critical, not only because it is important to our everyday life, but it's because many initiatives are going around the open source ecosystem now. That's it. Thank you, and sorry about having to break it up.
So,